Differential equations, we're in section 2.4, day 2, and we're going to be looking at exact differential equations. However, you can see this is also an initial value problem right here, as is very typical of our textbook. A lot of times we'll learn a method and then do an initial value problem as a second day. We're actually going to go further than that as well, but we'll see that in just a moment. Let's just say that you cross-multiplied real quickly, and you would get y times 1 minus x squared dy would equal this whole expression here, xy squared minus cosine x sine of x, and we have that as a dx. Let's bring this over to the left-hand side, and when we do, every sign will change. So this negative cosine x sine x will actually become a positive cosine x sine x. So I'll actually write that as sine of x coming first. This xy squared now is going to be negative, and we'll have this as a dx. And then, of course, we'll just add alongside of this y times 1 minus x squared dy. And why did we do that? Well, this is pretty much looking like what we've been seeing for our exact differential equations. We have function m multiplied to that differential dx, function n multiplied to the differential dy. So I'm going to do a little bit of work up here. We'd have the derivative with respect to y for m. You could see sine x cosine x goes away. We'd get negative 2xy. If we took a derivative of function n with respect to x, well, your parentheses here, 1 minus x squared, just becomes a negative 2x. You multiply that to your y, and you can see these are the same. In other words, this is exact. This is exact. And remember the motivation that we had for an exact differential equation. We were saying that if we had a function of x and y equaling a constant, it could be thought of as the derivative of x with respect to x, partial derivative of f with respect to x dx, plus the partial derivative of f with respect to y dy would equal 0. Why do I bring that up? Well, that's saying that m right here is your derivative with respect to x. So we could very quickly write that down. And as we are doing that, of course, we would say, well, I'd like to take an integral with respect to x to undo that derivative with respect to x, so to speak. Now we're going to have to do a little bit of review here. Obviously I'm talking about this right here, sine of x, cosine of x. As we take a integral right there, you might think of doing a u substitution, a little flashback from Calc BC. Let's maybe let u equal sine of x, du would be cosine of x dx. So this would be a u, cosine of x dx becomes a du. This becomes u squared all over 2 plus a constant, and that u then would be sine squared all over a 2. Well, why do I bring that up? Well, we have to take our antiderivatives here. So as we venture back over this way, we could say here's our f. This we just figured out was sine squared of x all over a 2. Take our antiderivative with respect to x here. This is x to the 1, bump it up to x to the 2, but then we have to divide by 2. And for a constant, well, remember that y is considered to be a constant in this regard, so we could say, look, there's some function with respect to y here. Speaking of that, as we go back to the motivation, the f of y dy, well, that's right here. We could say, now that we have this, let's take our derivative with respect to y. This thing is going to disappear, isn't it? A 2 is going to come down and cancel this 2, and we'd have a minus x squared y all over, well, the 2 is gone, isn't it? The 2 canceled that half. Sorry, our eraser is not working properly right here for some odd reason. There, I had to erase the whole thing, sadly. And then the derivative of g with respect to y is g prime of y. But what is that? Well, that's this thing right here, y times 1 minus x squared. I can distribute that, in fact, right here. And, then you can notice rather quickly that these two items, the minus x squared y, and this is another minus x squared y, could add a x squared y to both sides, and look at that. Things are cleaning up in a hurry. And then what? Well, we're getting so close, we can say g of y right here. As we take an antiderivative, this would become y squared all over 2 plus some arbitrary constant. Now, please do remember that we did find that f looked like so. And we just found out what g of y is. So I'm going to bring this over real quickly and say f was equal to sine squared of x all over 2 minus x squared y squared all over 2 plus g of y. Well, g of y is y squared over 2 plus a constant. And more to the point, remember the motivation that we had here, that f was really thought to be equal to some constant. So what we can do here is actually say, you know what? Here is the original equation that would satisfy that differential equation. And remember what drove this very thing in the beginning. We had y of 0 equals 2. Well, my goodness. Y of 0 equals 2. That means let x equal 0, while y would equal a 2. And what would happen? Well, you'd get sine of a 0 squared. Well, that's going to go away to a 0. Here's a 0 squared times 2 squared over a 2. That's going to cancel out. This becomes 2 squared all over a 2. That's your c. 4 all over a 2, so c equals 2. So guess what our final answer is really going to be? And this is what you'll see if you look in the back, is they're saying, could you write an equation that would satisfy that differential equation? And that's it. That's your f of x comma y is equaling some constant. Well, that took us a little bit of time, but let's continue to look on. It's not just finding an initial value problem that this section is working on. Very frustratingly, we might find that even though a differential equation might look like it's exact, it's not. You might find out that you could get the equation to be exact after multiplying by an integrating factor. So say this original differential equation is not exact. In other words, you go through the work, sadly, your m sub y is not equal to n sub x. Well, could we find an integrating factor right here, mu? Yes, we're going to talk about how. If you'd multiply both sides by it, you might then have an exact differential equation. So this right here is very important for us to just focus on rather quickly right now. Let's just say that you're not given an exact differential equation, but what if when you take m sub y minus n sub x over n, that you get a function of x alone? You no longer have y in that form. Notice that I've highlighted n sub x in green. That's because that second term in the numerator tells you what you hope that your function will be with respect to. You're hoping that when you reduce this, you'll have a function of x, n sub x, and notice your denominator then would be an n. So if you get that expression to be of x alone, then just like we did earlier in the chapter, where we normally found an integrating factor with a p of x, whatever that p of x was multiplied to our y in a differential equation, the function term. What you can see right here, if you work this out, you could get an integrating factor that could help you get an exact differential equation. By way of comparison, take a look at another possibility. If you change the order, n sub x minus m sub y, now your second term up on top is a derivative with respect to y. If this fraction is a function of y, then you're in business to get an integrating factor. Just like before, your denominator would also have to have an m, not a derivative, the original m function. And if you get this to work out as a function of y alone, then you could work out putting that expression only with y, e to that integral, you'll get an integrating factor. So it's a bit of work, but it's wonderful when you can get some help and definitely get some assistance. We're not going to be able to finish this problem in its entirety by this video, but we can certainly get started. Look, here's an m and an n. So I can very quickly take m and take a derivative with respect to y. You can see we're going to get an x. I can take an n and take a derivative with respect to x. Well, you can quickly see you'll get 4x. And this is where we can definitely get upset. We'll say, well, my goodness, this is not exact. Well, remember, we're going to subtract. We could take m sub y minus n sub x. Remember, that second term in the numerator, we're going to divide by an n here. We're going to hope that this expression is only in terms of x. You can see rather quickly it's looking promising until you throw in that denominator. And you could see, yeah, you'd get a negative 3x all over this. Sadly, it's no good. You could say, well, why isn't it any good? Well, you're not with respect to x alone, so that's a disappointment. We're not out of hope just yet. We could change the order and really hope that this alternative could work out. N sub x is 4x, m sub y is an x, but now your m is xy. Well, this is 3x over xy, and wonderfully, this is in terms of y alone. So this is wonderful news. This is what we had hoped would happen. So here's what we have to do. To find our integrating factor, we're going to go e of the integral of 3 over y dy. Now, it's only going to take you a moment to realize that if we just take an integral here, we would have a natural log with an absolute value. However, let's just consider for a moment that we're only looking at positive y's. And we'll talk more about that throughout our time. If that was the case, this would be e to the 3 natural log of y. And then we can raise up a power, property of logs. Another property of logs, this works out to just y to the 3rd. So what's our integrating factor? our integrating factor is y to the third. We'll pick this up in part 2.